Hi. In this problem, we'll be talking about communication across a noisy channel. But before we dive into the problem itself, I wanted to first motivate the context a little bit and talk more about what exactly a communication channel is and what noise means. So in our everyday life, we deal with a lot of communication channels. For example, the internet, where we download data and we watch videos online, or even just talking to a friend. And the air could be a communication channel for our voice. But as you probably have experienced, sometimes these channels have noise, which just means that what the sender was trying to send isn't necessarily exactly what the receiver receives. And so in probability, we try to model these communication channels in noise and try to understand the probability behind it. And so now let's go into the problem itself. In this problem, we're dealing with a pretty simple communication channel. It's just a binary channel, which means that what we're sending is just one bit at a time. And here, a bit just means either a 0 or 1. So essentially, the simplest case of information that you can send. But sometimes, when you send a 0, the receiver actually receives a 1 instead, or vice versa. And that is where noise comes in. Okay, so here in this problem, we actually have a probabilistic model of this channel and the noise that hits the channel. So what we have is, what we're trying to send is either a 0 or a 1. And what we know is that on the receiving end, a 0 can either be received when a 0 is sent, or a 1 can be received when a 0 is sent. And when a 1 is sent, we can also have noise that corrupts it and you get a 0 instead. Or you can have a 1 being successfully transmitted. All right. And the problem actually tells us what the probabilities here are. So we know that if a 0 is sent, then with probability 1 minus epsilon naught, a 0 is received. And with the remaining probability, it actually gets corrupted and turned into a 1. And similarly, if a 1 is sent, then with probability 1 minus epsilon 1, the 1 is correctly transmitted. And with the remaining probability epsilon 1, it's turned into a 0 instead. And the last bit of information is that we know that with probability p, any random bit is actually a 0 that is being sent. And with probably 1 minus p, we're actually trying to send a 1. All right, so that is the basic setup for the problem. And the first part that the problem asks us to find what is the probability of a successful transmission when you have just any arbitrary bit that's being sent. Okay, so what we can do here is use this this tree that we've already drawn and identify what are the cases, the outcomes where a bit is actually successfully transmitted. So if a 0 is sent and a 0 is received, then that corresponds to a successful transmission. Similarly, if 1 is sent and 1 is received, that also corresponds to a successful transmission. And then we can calculate what these probabilities are because we just calculate the probabilities along the branches. And so here, implicitly, what we're doing is invoking the multiplication rule. Okay, so we can calculate the probabilities of these two individual outcomes and their disjoint outcomes, so we can actually just sum the two probabilities to find the answer. Okay, so the probability here is p times 1 minus epsilon naught. That's the probability of a 0 being successfully transmitted, plus 1 minus p times 1 minus epsilon 1, which is the probability that a 1 is successfully transmitted. And so what we've done here is actually just looked at this kind of diagram, this tree, to find the answer. What we also could have done is been a little bit more methodical maybe and actually apply the law of total probability, which is really what we're trying to do here. So you can see that this actually corresponds to, the p corresponds to the probability of 0 being sent, and 1 minus epsilon naught is the probability of success, given that a 0 is sent. And this second term is analogous. It's the probability that a 1 was sent times the probability that you have a success given that a 1 was sent. And this is just an example of applying the law of total probability, where we partitioned into the two cases of a 0 being sent and a 1 being sent and calculate the probabilities for each of those two cases and added those up. Okay, so that's kind of a review of the multiplication rule and the law of total probability. All right, so now let's move on to part B. Part B is asking, what is the probability that a particular sequence of bits, not just a single one, but a sequence of 4 bits in a row is successfully transmitted? And the sequence that we're looking for is 1, 0, 1, 1. So this is how I'll denote this event. 1, 0, 1, 1 gets successfully transmitted into 1, 0, 1, 1. Okay, so now instead of dealing with single bits in isolation, we have a sequence of 4 bits. But we can really just break this down into the 4 individual bits and look at those one by one. So in order to transmit successfully 1, 0, 1, 1, that whole sequence, we first need to transmit a 1 successfully, then a 0 successfully, then another 1 successfully, and then finally the last 1 successfully. So really this is the same as the intersection of 4 different smaller events. A 1 being successfully transmitted and a 0 being successfully transmitted and 2 more 1s being successfully transmitted. Okay, so why are we able to do this, first of all? We are using an important assumption that we make in the problem that each transmission of individual bit has the same probabilistic structure. So that no matter which bit you're talking about, they all have the same error probability, the same probabilities of being either successfully transmitted or having noise corrupted. Okay. So because of that, it doesn't really matter which particular 1 or 0 we're talking about. And now we'll make one more step, and we'll invoke independence, which is the third topic here. And the other important assumption here we're making is that every single bit is independent from any other bit. So the fact that this 1 was successfully transmitted has no impact on the probability of this 0 being successfully transmitted or not. And so because of that, we can now break this down into a product of 4 probabilities. So this becomes the probability of 1 transmitted into a 1 times the probability of 0 transmitted into a 0, 1 to a 1, and 1 to 1. Okay. And that simplifies things because we know what each one of these are. The probability of 1 being successfully transmitted into a 1, we know that's just 1 minus epsilon 1. And similarly, probability of 0 being transmitted into a 0 is 1 minus epsilon naught. Okay, so our final answer then is just, well, we have 3 of these and 1 of these. So the answer is going to be 1 minus epsilon naught times 1 minus epsilon 1 to the 3rd power. Okay. Now, let's move on and go on to part C, which adds another wrinkle to the problem. So now, maybe we're not satisfied with the success rate of our current channel, and we want to improve it somehow. And one way of doing this is to add some redundancy. So instead of just sending a single 0 and hoping that it gets successfully transmitted, instead what we can do is send 3 zeros in a row to represent a single 0 and hope that because we've added some redundancy, we can somehow improve our error rates. Okay, so in particular what we're going to do is for 0, when we want to send a 0, which I'll put in quotes here, what we're actually going to send is a sequence of 3 zeros. And what's going to happen is this sequence is 3 zeros. Each one of these bits is going to go through the same channel. So the 000 can stay and get transmitted successfully as a 000, or maybe the last 0 gets turned into a 1, or the second 0 gets turned into 1, or we can have any one of these 8 possible outcomes on the receiving end. Okay, and then similarly, for a 1, when we want to send a 1, what we'll actually send is a sequence of 3 ones, 3 bits. And just like above, this 111 can, due to the noise in the channel, it can get turned into any one of these 8 sequences, any one of these 8 sequences on the receiving end. Okay. So what we're going to do now is, instead of sending just a single 0, we'll send 3 zeros, and instead of sending a 1, we'll send 3 ones. But now the question is, this is what you'll get on the receiving end. Now, how do you interpret, well, 000, maybe intuitively you'll say that's obviously a 0. But what if you get something like 010 or 101, when there's both zeros and ones in the received message? What are you going to do? So one obvious thing to do is to take a majority rule. So because there's 3 of them, if there's 2 or more zeros, we'll say that what was meant to be sent was actually a 0. And if there's 2 or more ones, then we'll interpret that as a 1 being sent. Okay, so in this case, let's look at the case of 0. The majority rule here would say that, well, if 000 was sent, then the majority is zeros. And similarly, in these two cases, 001 or 010, the majority is also zeros. And then finally, in this last case, 100, you get a majority of zeros. So in these four received messages, we'll interpret that as a 0 being sent. So part C is asking, given this majority rule and this redundancy, what is the probability that a 0 is correctly transmitted? Okay, so well, to answer that, we've already identified these are the 4 outcomes where a 0 would be correctly transmitted. So to find the answer to this question, all we have to do is find the probability that a sequence of 000 gets turned into one of these 4 sequences. Okay, so let's do that. What is the probability that a 000 gets turned into a 000? Well, that means that all 3 of these zeros had no errors. So we would have the answer being 1 minus epsilon 0 cubed, because all 3 of these bits had to have been successfully transmitted. Now let's consider the other ones. For example, what's the probability that a 000 gets turned into a 001? Well, in this case, we need 2 successful transmissions of zeros plus 1 transmission of 0 that had an error. So that is going to be 1 minus epsilon naught squared for the 2 successful transmissions of 0 times epsilon naught for the single one that was wrong. And if you think about it, that was only for this case, 001, but the case for 010 and 100 are the same, because for all 3 of these, you have 2 successful transmissions of zeros plus 1 that was corrupted with noise. And so it turns out that all 3 of those probabilities are going to be the same, so this is our final answer for this part. All right. Now let's move on to part D. Part D is asking now a type of inference problem. And we'll talk more about inference later on in this course. But for the purpose of this problem, what it's asking is, suppose you received a 101. That's the sequence of three messages, 3 bits that you received. Given that you received a 101, what's the probability that 0 was actually the thing that was being sent? Okay. So if you look at this, you'll look at it and say, this looks like something where we can apply Bayes' rule. So that's the fourth thing that we're covering in this problem. And if you apply Bayes' rule, what you'll get is this is equal to the probability of 0 times the probability of 1, 0, 1 being received, given that 0 was what was sent, divided by the probability that 1, 0, 1 is received. Okay, so we have this basic structure. And we also know that we can use the law of total probability again on this denominator. So we know that the probability that 1, 0, 1 is received is equal to probability of 0 being sent times the probability of 1, 0, 1 being received, given that 0 was sent, plus the probability that 1 was sent times the probability that 1, 0, 1 is received, given that 1 is sent. All right. And as you'll notice in applications of Bayes' rule, usually what you'll have is a numerator is then repeated as one of the terms in the denominator because it's just an application of total probability. Okay, so if you put these pieces together, really what we need is just these 4 terms. Once we have those 4 terms, we can just plug them into this equation and we'll have our answer. Okay, so let's figure out what those 4 terms are. The probability of a 0 being sent, well, we said that earlier. Probability of 0 being sent is just p. And the probability 1 being sent is 1 minus p. That's just from the model that we're given in the problem. Now let's figure out this part. What is the probability of a 1, 0, 1 being received given that 0 was sent? Okay, so if a 0 was sent, then we know that what really was sent was 0, 0, 0, that sequence of three bits. And now what's the probability that 0, 0, 0 got turned into 1, 0, 1? Well, in this case, what we have is 1 successful transmission of a 0 plus 2 failed transmissions of a 0. Okay, so that 1 successful transmission of a 0, that probability is 1 minus epsilon naught. And now we have 2 failed transmissions of a 0, so we have multiply that by epsilon naught squared. And now for the last piece, what's the probability of receiving 1, 0, 1 given that 1 was actually sent? Well, in that case, if a 1 was sent, what was really sent was a sequence of 3 1s. And now we want the probability that a 1, 1, 1 got turned into a 1, 0, 1. In this case, we have 2 successful transmissions of a 1 with 1 failed transmission. So the 2 successful transmissions will have 1 minus epsilon 1 squared. And then the 1 failed transmission will give us an extra term of epsilon 1. Okay, so just for completeness, let's actually write out what this final answer would be. So probability of 0 is p. Probability of 1, 0, 1 given 0 is, we calculated that as 1 minus epsilon naught times epsilon naught squared. The same term appears again in the denominator. Plus the other term is probability of 1 times probability of 1, 0, 1 given 1. So that is 1 minus epsilon squared times epsilon 1. So that is our final answer. And it's really just an application of Bayes' rule. Okay, so this was a nice problem because it represents a real-world phenomenon that happens. And you can see that you can apply a pretty simple probabilistic model to it and still be able to answer some interesting questions. And there are other extensions that you can ask also. For example, we've talked about adding redundancy by tripling the number of bits. But tripling the number of bits also reduces the throughput because instead of sending 1, you have to send 3 bits just to send 1. So if there's a cost to that, at what point does the benefit of having lower error outweigh the cost of having to send more things? And so that's a question that you can answer with some more tools and probability. So we hope you enjoyed this problem, and we'll see you again next time.